Hello all, my name is Vaisakh Shaj, and I'll be presenting the work Action-Conditional Recurrent Kalman Networks for Forward and Inverse Dynamics Learning. Motivation. Learning accurate models of robots can be challenging due to non-Markovian dynamics caused by hysteresis, unmodelled friction, stiction, contact dynamics, etc. Many actuators used in modern robotics violate the Markovian assumptions, including pneumatic soft robots, hydraulic robots, robots run by cable drives. We propose thus a probabilistic recurrent neural network architecture, namely Action-Conditional Recurrent Kalman Network, dubbed ACRKN, that can model non-Markovian dynamics accurately, is scalable enough to be deployed on data frequencies up to 1 kHz, allows principal treatment of control signals in the recurrent unit cells, and can learn both forward and inverse dynamics models. Let me start by explaining what a recurrent Kalman filter is. RKNs are deep, Gaussian state space models that can be trained end-to-end using backpropagation. These recurrent neural networks have a recurrent unit cell inspired by Kalman filter operations. RKN allows exact inference of latent states by propagating uncertainties through Kalman filter operations. The predict step of this Kalman filter uses locally linear state transition similar to extended Kalman filters. And the update stage of the RKN cell have factorization assumptions which avoid computationally expensive matrix inversions, thus making the entire approach scalable. Action conditioning is a critical component for learning dynamics, and most existing approaches achieve action conditioning by treating control actions as fake observations, which is not principled. ACRKN, on the other hand, captures the causal effect of the control action on the state transition using an additive control factor called P of 80, as shown below. P of 80 need not be linear or locally linear like the state transition matrix 80, but can use an expressive global nonlinear function approximator like a neural network. This allows disentangled state and action representation in the RKN cell. We use this for both forward and inverse dynamics learning. In case of forward dynamics learning, we decode the prior, while in case of inverse dynamics models, we decode both the prior and the posterior. The prior beliefs are decoded to get the next state observations, while the posterior is decoded to get the predicted torque. The action decoder also gets the next observation or state as an additional input. Note that in the inverse dynamics model, we also feed back the executed action by the robot to the predict cell, which helps in getting much better prior beliefs. Also note that the inverse dynamics model has an additional forward loss in addition to the inverse loss, which acts as a regularizer. In our experiments, where we have to deal with high frequency data, we predict the differences to the previous observations and actions. Experiments. We perform multi-step ahead forward prediction on robots involving non-Markovian dynamics like pneumatic soft robots and hydraulic robots. As you can see in the figure, ACRKN outperforms the current state-of-the-art recurrent and non-recurrent models like LSTMs and feed-forward neural networks on this multi-step ahead prediction task for both robots. Also, it outperforms the naive RKN, which treats actions as fake observations, thus reinforcing our principled action conditioning. We also perform joint torque predictions on a Barrett-Vam robot run by cable drives using the inverse model and achieve state-of-the-art performance compared to other deep models. Also note that the action feedback at the predict stage of the inverse model helps us in making better predictions. We also perform additional experiments on Franco-Amiga Pandya with data frequencies up to 1 kHz and make comparisons also with the rigid body dynamics model of these robots. And notice that we get much better performance compared to these textbook rigid body dynamics models. In conclusion, we introduced ACRKN capable of action conditioning within the recurrent cell in a principal manner, has a disentangled state and action representation in the recurrent cell, can learn both forward and a regularized inverse dynamics model, is capable of dealing with non-Markovian dynamics, and can perform scalable inference that can handle data frequencies as high as 1 kHz. As a future work, we'll use this for model-based reinforcement learning. Also, we will apply the ACRKN dynamics models for real-time robotic control and investigate generalization capabilities to unseen workspace configurations. Thank you for listening.